Hi, and welcome to AWS Summit Online. My name is James Wenzel. I'm here to talk about getting started with AWS networking, setting up secure networks that are monitored across the globe. Welcome again. Let's get right to it. Here's the agenda of what we're going to be discussing. First, we'll talk about how AWS networking works and set up a network. Then we're going to talk about connectivity, both inside and outside of AWS. Then we'll be discussing DNS, domain name systems, and then how to monitor our networks. So many of you probably have seen this slide, and this slide is a build out of a working 3-tier web app using public AWS constructs. We have our network set up with a load balancer, we have multiple subnets and multiple AZs, and we're gonna break this all down. There's a lot going on here. So let's help build this up. First, we got to start and talk about the AWS backbone. The AWS backbone spans the globe. We have our own fiber. We have lots and lots of data centers across the globe. These data centers are not out there with huge AWS signs or anything. They're pretty discreet for obvious reasons and security. All the fiber that you see on this diagram shows connectivity between different continents. Everything under the sea, that's all AWS. It doesn't belong to anybody else. We're not using any other third parties. So we can be sure that our network has enough bandwidth and has enough capacity to carry our customers. This also allows us to monitor this network and monitor the backbone to allow it so that our customers, when they grow, we can stay ahead of them so we don't run out of resources. As you can see here, we also mentioned we have 25 different regions, and regional constructs, which we will explain in a little bit, are across the globe that are a conglomerate of data centers that we have in a specific spot. We also have 81 availability zones, which go into the regions. We'll discuss those as well. And then some extra constructs, which we're not talking about today, but I'm sure there are in other discussions and other presentations within the summit, are local zones, which are edge networking within major metropolitan networks, wavelength zones, which will get you onto the carrier networks like 5G and connect your workloads directly to that. We have 108 direct connect locations. We'll be discussing those as well. And then we have 230 plus points of presence. And these points of presence are where a lot of our constructs get as close as possible to our customers. So let's talk about regions. Regions are located around the globe, but we're just showing a snapshot of the United States. And these are larger areas where we have multiple AZs or availability zones, and we distribute them as close as possible as we can to major data centers. We also make sure that these regions are located in areas that are densely populated or where a lot of users are going to be, and we make sure that the regions are secure and redundant. So now that we have a region, we need to do something with it. And regions have to be populated, are always populated with availability zones. But there's another thing that also operates within a region outside of that, and those are our public-facing services. So S3, DynamoDB, Lambda, and more are actually located within a region that can be contacted with public IP address space. Some of these constructs can be actually used internally to our workloads without going over the public internet, but can also be exposed to the public internet to make it easier for your customers to consume your services. Now that we have regions, we need to add something called a VPC, or a virtual private cloud. A VPC is an area or a boundary that you set up around your workload and around your network that keeps everything private and only allows ingress and egress to that network on your level or your control. So if you want someone to come into your network, you have to explicitly allow it. And if you want something to go out to the internet, you explicitly have to allow it. This doesn't put anything on the public internet at all. It just sets up a boundary and it gives you guardrails, if you will, to make sure that your workloads are secure and all of the network traffic and flow can be monitored within that VPC. So the first thing you do when you have the VPCs, you have to give it an addressing scheme. So you'll have to give it an IP block. You can give one or more IP blocks to this addressing scheme, but it's important to take note to use some form of IPAM or IP administration Make sure that you don't have any overlap or any cross addresses. And if you're going to be using any type of public addressing, which sometimes needs to be done, that it's not actually in existence somewhere else out on the internet. After we add the IP addressing block, we want to add our AZs, or our availability zones. The thing to note about AZs is they are actually one or more data centers that are on their own fault planes, they're fault tolerant, they have their own power, so that none of the power is shared. And this is to keep any type of outage from affecting your entire workload within a region. So if we have an AZ failure, then you would still be able to operate on another AZ within the same region. It wouldn't take everything out. All of the connectivity between AZs, which is using high throughput fiber with low latency, is also encrypted. Every time we leave our data centers, or anytime we go between our constructs of different AZs, we want to make sure that the traffic is secured as much as possible. So on top of your AZs, you would start building subnets. Each subnet, of course, would have an IP address scheme that you give. You can add, in this case right here, a public subnet and a private subnet. And the concept of a public subnet is something that you would expose, say, to the internet. You would have maybe some instances or some services that you want to have directly contactable by the internet. And then when you have a private subnet, that is something that would only communicate to the public subnet or communicate with each other, and would not allow the internet to actually access this. This gives you your defense in depth, or many layers of control. So then once you have that subnet, you'll start launching those instances. Each instance then will sit and inherit the IP addressing scheme if you turn on the ability for your VPC to administer IP addresses. If you do not, then you would actually have to add your IP addresses to each of the instances yourself or manually. One other thing too to mention is within this region, we are showing that we have 2 availability zones available, but there are sometimes many more than 2. It can be up to 3. Some of them have more than that. We strongly recommend that when you're launching your instances, that you launch a pair in each availability zone. This again will go back to taking advantage of all of those availability zones, redundant power, redundant locations, fault tolerance, the issues of having an AZ going down will not negatively affect your workload. So you will automatically inherit the HA and redundancy if you use each of the availability zones out there. The next thing we would add to be able to give our instances or our EC2 servers or our workloads access to the internet is something called an internet gateway. An internet gateway will provide network address translation, or NAT, back and forth between your instances and your public subnets and the world. In this example here, I'm using 2 elastic IP addresses, or EIPs, for a 1-to-1 NAT. This will give you bidirectional access. So in other words, you're actually taking those instances that are in your public subnet and allowing it to speak to the internet, and you're allowing the internet to speak back to those instances. Now, one question it might ask is, wait a minute, you're giving bidirectional access. How do we protect ourselves? How do we make it so that someone can't get access to one of our instances or one of our machines running on the public network, so that they can do something nefarious? So we have security groups and network access control lists as a form of defense against this. There's some fundamental differences between security groups and access control lists. Security groups act as a virtual firewall. They are stateful, and they allow the responses that go out to come back into your network, and they are applied to your instances, or your ENIs, elastic network interfaces of your instances, and they're also applied at the VPC level. You cannot launch an instance without having some form of security group actually active. The security groups has a limit of around 25,000 per account. So then you can also strategize as to how you want to share them, or if you want to have them unique. It is always important to look at your security groups and say what kind of security strategy you want. If you have a group of EC2 instances that can share the same security group, that's preferred. But keep in mind that when you make a change to that security group, all of those instances are affected. So you want to really have a good strategy for that. The second thing that we have is network access control lists, or NACLs. NACLs are applied at the subnet level, and they are stateless, which means that if you allow something to go out of that subnet to the internet or to somewhere else within your workload, you need to also explicitly allow it to come back. Now, these are all on by default, these network access control lists, but they are actually set to be default open. So you need to have, again, a good plan as to how you want your security to look on network access control lists if you need to actually get down to a stateless security posture or use the stateful security posture of the security groups alone. But remember, the security groups are actually going to be on no matter what. And then your network access control list, you can actually start ratcheting down those rules. You could, in effect, take a network access control list and make the rules so stringent that the security groups, even though they may allow traffic, the network access control list on the subnet level will actually deny that traffic. So how do we get our private network interfaces or our private network EC2 instances out to the internet? We would do that with a NAT gateway. So that would allow you to do a more or less port address translation or many-to-one NAT out to the internet to get patches or whatever it is that your systems need to do. But it does not allow any of the network traffic or internet traffic to come back on an initial request. So again, this is a stateful standard network address translation procedure, but it allows it to come back. Another thing that we've released, which is newer, is the ability to do private NAT gateways. And what this does is instead of going back and forth to the internet, the private NAT gateway will allow you to actually go back and forth to different parts of your workloads or your constructs. If you have multiple VPCs or if you have other connectivity through, say, something like a transit gateway, and there's maybe a merger that had happened and someone has the same overlapping IP blocks as you do, it's very difficult to actually have that connectivity take place. So you can actually take advantage of private NAT to facilitate that, maybe set up another IP block in your VPC that's not an offending or the same IP block as the network you're trying to connect to. Use that as your connection point, and then you can put a private NAT in between those two so that you can actually facilitate communications back and forth. Now, all these different constructs are great, but we have to talk about routing. What does routing look like? So each one of your VPCs has a routing table. That routing table is what we call the default routing table for the VPC. And of course, you can add and remove things within this routing table as you need. But keep in mind, as you're editing that routing table, it affects everything inside the VPC. Anything that you're launching inside of a VPC can naturally talk to each other automatically through its local interface. So if you're going to be adding different pieces of connectivity, if you're going to be adding VPC peering, which we'll be talking about, or a transit gateway, you're going to have to, in essence, change that routing table to allow traffic to come in and out. The other place that you can actually put a routing table is on a subnet. Now, we recommend that you actually use those subnets for your configurations and changes, because if you have multiple subnets, as I mentioned before, this is very, very common to have a public and a private. You don't want to have all of your EC2 instances be affected when you make a change on a larger routing table, such as on the VPC. If you start using the smaller or lower blast radius routing tables on the subnets, and you have to do adds, moves, and changes to a particular subnet, it doesn't affect all of the rest of your workload. And it gives you an easy way to actually go back and troubleshoot. So instead of direct accesses to our instances, before we were showing the one-to-one EIP NAT to our public instances, there's another way of handling this, as well as giving us elasticity and the ability to actually send traffic to our back-end systems without overloading one or the other. And that's to introduce load balancing. Here, I'm showing an elastic load balancer, or an ELB, that is representing two instances, instance C and instance D, and it will accept that traffic through a interface that actually is on the internet through the IGW for you. Now, some of these load balancers will give out a endpoint which can have multiple IP addresses, but is attached to an FQDN, or a fully qualified domain name. That FQDN can then easily be CNAMEd into DNS, so it could be www.yourcompany.com. And then some of the other Elastic load balancers will allow you to add a static IP address. These load balancers do not always have to have internet access either. You can actually use them internally. So in this example, I'm showing a simple external to internal load balancer, but you can also do internal to internal load balancing as well. So let's talk a little bit about our Elastic load balancing. We have three types that I'm going to talk about today: the ALB, or Application Load Balancer, the Network Load Balancer, or NLB, or a Gateway Load Balancer. The last type that I'm not mentioning here is the Classic Load Balancer, which operates at 7 and 4, but at a very limited set. So what we're trying to do is we're trying to get our customers to move to one of these more advanced load balancers, as opposed to the older Classic Load Balancer. So let's talk about the Application Load Balancer. When we're looking here, an Application Load Balancer does exactly as what the name suggests. It operates at layer 7. This will support any type of connectivity even to Kubernetes. You can do direct-to-pod targets. This will give you gRPC routing, HTTP2, as well as standard HTTP. You can do header-based routing, which is great. And for added security, the ALB also integrates with WAF, or a Web Application Firewall, which then at layer 7 can monitor and keep things from happening, like cross-site scripting or any type of URL mangling. So it's a very good load balancer to use in front of Kubernetes pods. It's very good to use for any type of strong HTTP type traffic. The next type of load balancer we have is a network load balancer. The network load balancer operates on our hyperplane. It is a very, very fast, low latency load balancer. Layer 4 is typically what we say it operates on, and it uses TCP and UDP. One thing to mention too with the NLB as well as the ALB is both of them do TLS termination, so it can do that offloading of the TLS traffic, so you don't need larger instances to be able to process that. But the NLB also does some other cool things too that the ALB does not. One of the things that the NLB does is it allows for private link, which is a form of interconnectivity with other VPCs within the AWS network. And it allows for that traffic to traverse across the backbone. And as you can see in the example here, where I'm showing on the right-hand side that we're doing private link, it will help you get around any type of IP overlap. You'll notice that the VPC on the right has the same type of addressing as the VPC on the left. That's because the way that the NLB operates, it uses the ENI, or Elastic Network Interface, the little purple things. It uses their ID for communications as opposed to the IP addresses. And each of those ENIs will actually get a local address to each of the subnets. So everything works out well. And then the last one is a gateway load balancer. Now, the gateway load balancer is very different from the ALB and the NLB in the fact that it is not something that you would put and expose to the internet to be able to route traffic back and forth to your targets for your workloads, as much as it's for putting in front of IDP or firewall type devices that will be inspecting traffic. The way the gateway load balancer works is it uses endpoints, and then you put them into your network, and you can actually shape the traffic to go using something like ingress routing, where you can put a routing table on your IGW and forces the traffic through the gateway load balancer into those devices, and they can have auto-scaling groups so that your firewalls or your IDPs can grow and shrink based on your needs. In general, the gateway load balancer works basically by encapsulating the packets entirely with Geneve protocol, so that the source, destination, and payload are absolutely preserved, and source and destination that are actually using that packet never know the wiser. It is important to note that if you're going to use something behind a gateway load balancer, make sure that it supports Geneve. You can find a lot of our partner solutions on our marketplace that automatically support the gateway load balancer, or if you're going to build something yourself, using, say, Linux, make sure that Geneve is there. So let's talk about internal connectivity. We have three different types that we're going to talk about today: peering, a transit gateway, and AWS Private Link, which we discussed a little bit already. So when we're talking about peering, what we mean by that is we have multiple VPCs, and those VPCs want to communicate. And because of the type of traffic that we have in AWS, with the whole transitive and non-transitive nature, we do not allow or do not support a packet going from one VPC to another VPC using a natural AWS construct that will then pass into the third. To give an example or to make that more clear, if you have traffic starting from VPC A here and it goes to VPC B, it will not easily or cannot pass through link number 2 to VPC C. A has to connect to C itself. That's because when the traffic or when the packets pass between different VPCs, we don't have any routing type device that's actually replacing the source with itself to allow each hop to continue down the path. So when a packet goes from A to B, whatever instance receives that packet, knows that the source IP address is actually in A, not a router to A. So if we're adding any more on top of this, we have to make sure that we have our routing tables. So we show here, B has a routing table that needs to be replicated to all of the others that have routes for every connection. So if we want to actually add more, like say a D or an E, we have to build a full mesh. And that full mesh has to be represented in each routing table of every VPC. VPC peering can also happen cross region. So from one side to the other, everything operates and works well. But to keep note that if you're going to go at scale, you're going to need to do something else. So some considerations for VPC peering is that if you're doing a full mesh network, again, you need to make sure that you update all the routing tables. And the maximum number of peers per VPC is 125, and you cannot have any overlapping IPs unless you do something, as I mentioned before, with the private NAT gateway and something special with the multiple IP blocks. Now, the next thing that we can move up to is the transit gateway, which will allow you to scale up to 5,000 VPCs, as well as allow you to connect, direct connect, as well as VPN to your transit gateway. And the way that the transit gateways operate are through associations, propagations, and routes. You can associate multiple links or a single link to a route table, and then you can propagate to multiple locations and then assign each route. Some considerations with transit gateways, again, you can connect up to 5,000 VPCs, and you initially get 5 of them per account. One of the things is you cannot have overlapping IPs, and again, unless you're trying to use some sort of private NAT. And whenever you're making them, we always say, please do not reuse your ASNs or your system network, your system numbers, autonomous system numbers, because of the fact that when you're adding multiples, we use BGP as a way to communicate in the background. And if you're going to set up multiple TGWs with the same ASNs, the BGP protocol won't know how to route that back and forth. So always make sure that you're using a unique ASN for each TGW. So the other type is the private link. Remember, that uses NLB if you're setting up yourself, but private link can also be attached to some of the public services. You'll remember in the first slide, I had some of these public services available, and there's 2 different ways to do it. There's the gateway endpoint, which basically makes a change to your routing table. So when you enact a gateway endpoint, there's nothing else you have to do. Everything inside your VPC will automatically use the routing table to communicate. The other type is the interface endpoint, and this is where you can also affect your own by using the NLB. The interface endpoint uses an IP address that is attached to a local ENI on that network to communicate over the AWS backbone. One of the things you might have noticed is that Amazon S3 is highlighted both times. Amazon S3 is a special case where we have both the gateway endpoints as well as a private link endpoint or ENI endpoint or an interface endpoint, so that you can communicate, say, through your direct connect or your VPN to on-prem or from other locations, because it gives you a routable IP address. If you're using a gateway endpoint, it is only accessible by those constructs inside your VPC. So showing here, we have private link, which is a unidirectional flow from the endpoints that are in the consumer account that are attached to the network load balancer and its services behind the load balancer in the private account or the provider account. So as you can see, the packets are flowing from the consumer to the provider, and it cannot go in the other direction. Also to note, each of those ENIs that are in the consumer account can have a security group attached to them, or they will absolutely have a security group attached to them, and you can use that to, again, further your security. Just make sure that those security groups actually have the same ports open on them as the listeners that you configure on your network load balancer. So now let's talk about our external connectivity. We have VPN, site-to-site and client, and Direct Connect. So for our site-to-site, we have our on-premises, we have our customer gateway and our virtual private gateway, and we're going to go over the internet. We have 2 tunnels at 1.25 gig. We have a primary and a secondary, and all of the communication usually happens over a primary tunnel, which is restricting down to 1.25 gig. If there's a failure, it will go over to the secondary tunnel. The other things we can do is we can connect this to a transit gateway. The transit gateway will allow for ECMP. ECMP, or equal cost monthly path, will allow you to actually go up to 50 gigs burstable on all of the different tunnels. And then, of course, you can reach all of your 5,000 VPCs that are connected to the transit gateway. The other thing noted is that if you have transit gateway peering between one region or another, you can actually reach all of those through one transit gateway. So you can plan out your network accordingly. And then the last thing we have is the VPN client. This is a way to get your users, using the OpenVPN client, connectivity to the rest of your workloads. It uses a TLS-based tunnel over the internet, and it uses an ENI, or an attachment base, to a VPC. This will give you access to all of your different constructs, to S3, DynamoDB, your public services. It could even give you contact to on-prem networks if you're using, say, a Direct Connect or a VPN, depending on how you route it. So let's talk about Direct Connect. I've mentioned that a couple of times. This is basically a service where you connect your on-prem to your AWS region or your AWS VPC. This requires you to use some form of partner that we have in our Direct Connect program to give you that last mile. So the service provider will give you that fiber to your location. There's a Direct Connect location where they, your partner, will have a cage with AWS equipment in it, and then a cage with your equipment that you could typically lease, or you can even put in yourself. And then that will facilitate connectivity to a VGW within a VPC over a private VIF, or it can give you communications over a public VIF. The public VIF gives you a public IP address and allows you to directly access things like your S3 buckets in DynamoDB. The other thing you can do, and keep in mind, is add on more and more connectivity with a dedicated connection, because you get up to 50 virtual interfaces that are either public or private, and you get one virtual interface that allows you to actually connect up to a transit gateway called the TVIF. Now, if you have 50 and you need more, you can use something called a Direct Connect gateway. The Direct Connect gateway will give you an ability to break out a private interface from 1 to 10 interfaces, and it will span multiple accounts and around the globe. So if you want to use one Direct Connect to access multiple constructs around the globe, you can use a Direct Connect gateway. The other thing that a Direct Connect gateway allows you to do is to connect to a transit gateway, and that transit gateway then can connect up to your 5,000 VPCs, it can connect up to multiple accounts, all of that fun stuff. Now we're going to talk about DNS. Route 53 DNS is a very powerful construct that allows you to set up and configure DNS names for your workloads. It's fully compliant with IPv6, and also you can use something called resolver endpoints to allow your on-prem to resolve back and forth to and from, or forward back and forth, your on-prem DNS to DNS in AWS. There's a lot of features that it has, but a couple that I want to call out that we have recently released is DNSSEC support, as well as the resolver DNS firewall to protect recursive DNS. Route 53 considerations as well, as you can have up to 5,000 hosted zones per an account, and you can have full resolver endpoints. And these soft quotas are things that you can ask your solution architect and account team to help make larger, and then your hard quotas, of course, are restricted. And then the last thing we're going to talk about is monitoring today. There's many different places you can monitor. One of them is in Amazon CloudWatch, and CloudWatch basically is an account-based monitoring setup. The next is VPC flow logs, which with enhanced flow logs, you can actually manipulate and add and remove fields. But to quickly walk through that, so this is what we would see in a standard flow log. So you can see what account ID is actually being used within the flow. You can see what IP interface or ENI interface ID is. You can find out what port and protocol it's going for, and if it was accepted or not. This can all be sent to your SIEM through S3 buckets or through CloudWatch, and you can then consume it there. CloudTrail is another thing that we always want you to turn on, which basically shows any type of API access back and forth in your account, so that if anything was done, you know who, what, when, and where, and how. That is all recorded within a log. And then we also have a service called traffic mirroring, which is a lot like the old port spanning that we used to use on-prem, where you can actually mirror the traffic of an interface and get down to what the payload is, as long as it's not encrypted. We do have some partner services that actually will let you decrypt and look inside as well. So if that's needed, then please go ahead and use it. And then lastly, we're going to talk about infrastructure as code. One of the things that's important to note is that when you're building these networks on AWS, you want to make sure that you can react with changes, you can actually troubleshoot quickly, and the way we do that is through infrastructure as code. Whether you're using Terraform or CloudFormation, we strongly encourage that you do it in this manner. It allows you to do rollbacks quickly, and it allows you to do adds, moves, and change quickly. So whenever you make any type of improvements, you can actually record those, and then you can add it to your automation to do the rollout for the creation of these things. This allows for things like rapid rollout, and then you can also, again, troubleshoot and recover quicker. Once you do that, you can capture all that metrics and things in your lessons learned, and then go back in and improve your cycle. Now, to learn more about AWS networking, we do offer training and certification courses. They're free and online. Plus, you can get the AWS specialty certification, and there's even a book on Amazon that is written by some of my colleagues that is really good at breaking down and going much deeper into all these services. Thank you again for attending this session, and please don't hesitate to give any type of feedback. Let us know how we're doing, and let us know what you'd like to see in the future.